Okay, thank you. The next talk will be by Todd Holland, AI-based molecular classification of diffuse gliomas using rapid label-free optical histology.
Excellent. All right, thank you so much for the opportunity to speak. So I'm going to be talking about how we can use artificial intelligence to improve diagnostics and particularly make it more accessible and rapid. So 2021, WHO comes out, it classifies diffuse gliomas using molecular features. And now we really just have 3 types of diffuse gliomas in the adult subgroup. That's astrocytomas, oligodendrogliomas, and glioblastomas defined using IDH and 1p19q. We know that if we use these molecular features, they stratify patient survival and treatment response much better than histopathology alone. And our conventional workflow has been very similar for nearly a century, where we get a specimen, surgical specimen, whether it's a biopsy or tumor resection, it goes to a pathology lab, and then it undergoes a battery of both histologic and molecular tests. Those are all integrated using a neuropathologist or a team of people in order to integrate that into a single diagnosis that gets rendered at some point in the future, up to 1 week to 6 weeks, depending on the lab and how seamless this workflow is. For example, methylation testing still at the University of Michigan takes 6 weeks as a send-out test. And what we're trying to do is actually develop a parallel screening workflow that allows us to render a diagnosis in about a minute in the operating room. And we do that using stimulated Raman scattering microscopy. So this is the microscope right here. This is what lives in our operating room. We have 2 of these, and there's now about 10 distributed across the United States and Europe. And we get high-resolution digital images in the operating room. This is not whole slide scanning. These are not H&E images. These are actually digital images that are acquired through the stimulated Raman scattering effect. And then what my lab focuses on is how can we use computer vision and artificial intelligence models to interpret these images in hopes to predict the actual molecular diagnosis that is diagnostic for these tumors. So that's what this talk is about. So why is this important? We do know now that the efficacy of extended resection is different depending on which molecular subgroup you are in. There is some newer data coming out that if you're a molecular astrocytoma, you benefit significantly more from potentially a supramaximal resection compared to an oligo or a glioblastoma. None of this information is available to us in the operating room as surgeons. And then there was an excellent review that came out this year by Craig Horbinski in Nature that was really talking about now with the update in 2021, we do need to think about more accessible and timely molecular testing. And then ultimately, I think one of the most important things is, say you want a clinical trial that requires delivery of, let's say, an oncolytic virus at the time of surgery, and you want to only enroll patients with in a specific molecular subgroup, that study is going to be rejected by the NIH because of feasibility. So really, we don't have the opportunity to do those studies at this point. So the real reason I did this, though, was really for the scientific value, and that is I think we as humans have the presupposition that we're able to extract all of the information in our visual world. And I think that's just a false assumption that we all have. We see all the things that we can see, but I think there's a lot of other things available in our visual world, particularly with high-dimensional, complicated, semi-quantitative optical imaging. I don't have any reason to believe that I'm adept at interpreting those images, and that's part of the reason why we as humans can't make strong assumptions about whether the patient is ATRX mutant or IDH mutant. And these images are wildly complex, right? This is just an example of some low-level image statistical things that we can do, like a simple thing like a Fourier transform, we don't see in frequency space, right? All of these are simple analyses that you can do, but of course we don't want to define these things. We want these to be learnable features that are able to be detected by a trainable artificial intelligence. And that's what my lab had done. So we trained this model called DeepGlioma, which can unlock these molecular diagnoses. So how do we do that? We do it in 3 stages. We first learn the images, we learn the genomic landscape, and then we learn how to classify those images using the genomic landscape. So this is one of the technical contributions in the papers. How do we train these? Patient comes in, gets a tumor or a biopsy. This is the image that we get in the operating room. And again, these are falsely stained. These are an artificial staining. This is not H&E. But you take two images that have the same molecular genetics. You pass it through a deep neural network here. This is the same deep neural network. And you get an embedding vector. So this is some fixed dimensional vector. You can think of this as a row in your Excel spreadsheet. And then ultimately what you want to do is you want to optimize this function. And here you can say this is in the numerator, so this would be Z1 and Z2. You want to make this inner product as large as you can, and then you take a whole bunch of negative examples. These are patients with different molecular genetics. Those go in the denominator, and you want to make that number as small as possible. So this number big, this number small. And you do that a couple of billion times, right? GPUs don't get tired. And you can do that over your full data set. And ultimately what it does is learn to extract the features that ultimately predict the molecular genetics that you're interested in. So that's how we learn the images. We know the genomic landscape. That's been published. TCGA, CGGA, excellent public repositories. So for example, we know that if you have an IDH mutation, there's a high likelihood that that's going to co-occur with either 1p19q co-deletion or an ATRX mutation. But if you're just showing the model images, it doesn't know anything about these co-occurrences. So it gives us some prior knowledge about what certain things should co-occur, what classification events should actually co-occur, and that's what we were able to do with some pre-existing data. And then this is it end-to-end. So image comes in, we get this whole slide image. Here, we cut it up into individual patches. We put it through, basically this is the infrastructure for the model, the actual architecture. And then you output a probability distribution over each one of the different mutations that you're interested in. In this case, we did 3. And then you can actually get a WHO granular whole slide image heat map for each one of the molecular subgroups here. So this is an example of an oligo. And this is something that we get in the OR. Now that's the easy part. The hard part is actually testing it. So we did it at 4 medical centers, 2 in the US and 2 in Europe, UCSF, NYU, Cologne, and Vienna. And we did a power calculation. We needed at least 147 patients to validate this, and we got 153. And these are the results. So overall, they were quite good. We were over 90% for all the classification metrics that we looked at for each one of the mutations, IDH, 1p19q, and ATRX. And again, this is in our prospective group. This data was quarantined from us prior to training. And then how does this work in the real world compared to the first level screening, which we do in all patients? And this is an example. R132H immunohistochemistry is, for the most part, standard of care for screening for IDH mutations and diffuse gliomas. We were able to beat that. So see, basically, if you look at all patients, if you look at balanced accuracy, which is just the average between the sensitivity and specificity, we were able to improve over immunohistochemistry by 3 points. If you look at young patients, which this room knows, if they're less than 55 years old and it's a negative R132H test, those must be sent for sequencing because the false negative rate for immunohistochemistry is so high. So how do we do now for the multi-class classification? This is each one of the molecular subgroups. We were able to do quite well here, again, over 90% accuracy. So this is the advantage, really, in my mind. So how do we do a non-canonical IDH mutant prediction? So this is a patient that had a IDH2 mutation, and we were able to accurately predict that this is, in fact, a molecular oligo with an IDH mutation, despite being a negative immunohistochemistry. And we have a website. Please visit this. My data scientists worked hard on this, so you can look at this and you can look at hundreds of different cases and different heat maps and predictions that go along with this study. And this is my group. I run the Machine Learning and Neurosurgery Lab at the University of Michigan. I definitely have to thank all of my collaborators. Thank you very much.
Probably time for one question.
Could you comment on your training data set?
I didn't catch that.
Could you comment on your training data set?
Comment on the training data set?
Yeah, like
yes.
How big of a training data set did you
Excellent
use?
question. We had 373 patients in our training data set. They were all University of Michigan patients, so we always take an external testing approach. I don't like ever testing at our institution, but we had about 373 patients that were acquired over the course of about 5 years or so.
Thank you.